Good morning, everyone. Happy weekend. Thank you so much for joining our session. It's a knowledge learning session. Saturday morning, every weekend is the best to learn. And this week, we are joined with Todd Sullivan, all the way from the US, and it's almost midnight there. So very, very much appreciated. And he's a NASA Solar System Ambassador. And today he's going to teach us about Lucy, the latest NASA mission to the Trojan Asteroid. So I find it very fascinating. So it's a deep space exploration mission, and there's so many sensors, instruments on Lucy that's going to places we've never explored before. So we don't want to waste our time. So I'm going to let Todd take over the virtual room. And if any one of you wants to ask question, put it on the chat box. And once we come to the Q&A session, turn on your video and you can ask Todd yourself directly. Okay, there you go, Todd.
All right, good morning, everybody. Everybody hear me? Are we good?
Yeah, the sound loud and clear.
All right, thank you very much. So as Ann said, my name is Todd. I am living in Pennsylvania right now, about 1 hour outside New York City. And I've been a volunteer for NASA for 14 years. And I think a lot of people took a break during pandemic. And so this is my first one in about a year. So I'm very, very happy to be with all of you. I'm very happy that Ann found me and reached out to me. It's as we say in the United States, it's good to be back in the horse saddle again. It's good to be back on the horse. So so today we're going to be talking about Lucy. It's a mission that launched recently. The mission in its entirety is going to be 12, or as you will find out, many more years. So having said that, if I don't know the answer, I'm sure Ann will help kind of document the question for me, and we'll certainly try and get you the answer afterwards. I am certainly not a chemist by nature or such. Just with a fascination and excited to share. So let's get started. So first off, I'd like to talk a little bit about imagination. You know, I'm a world traveler, and a lot of us have seen different places, and we've gone to different places where, you know, we wish we could have, you know, been there at a different time. You know, I've certainly visited some ancient sites around the world, and you know, sometimes I sit there and I'm looking around at the buildings, and I'm like, man, I'm sitting on steps that have, you know, people sat on these steps thousands of years ago, and wouldn't it be great to kind of go back in time and, you know, see the vibrant city and see the color on the temples and the buildings, people milling around. What are they saying? What are they talking about? What are politics like at the time? What's the philosophy of the time? You know, way back when, you know, it would just be awesome to be able to go back and, you know, kind of experience that. You know, hey, they're building these buildings, you know, what are they building it with? What are the building blocks? Wouldn't it be awesome just to take a piece of that home with you and be able to study it? You know, if you could just freeze, you know, that period in time whenever you wanted, so you could go back and visit it. You know, you could interact with the people, the food, and the period, and the history. So I'm a world traveler, and I often think about those kind of things. Is what was this like 1,000 years ago, 100,000 years ago, 1,000,000,000 years ago? So, you know, wouldn't it be great, again, just to freeze that time and period, and, you know, really just take a sample of, you know, what built the solar system? How did it come to be? How did the Earth come to be? How did we get our water? How did we get our air? Why is Mars the way it is? Why is Venus, a runaway, greenhouse effect planet? So again, I'm thinking that would be really, really cool if we could go back. I could go back 4 billion years and take a sample rock, and put it in a time capsule and bring it back forward to the time with me. And let's analyze the building blocks of the solar system. Well, the beautiful thing about astronomy is you can actually kind of do that. And that's what this mission is all about. It's really kind of a space archaeology, going back in time. And instead of, going back on Earth and finding the oldest rocks on the planet, we're going to find the oldest rocks that built the planet. So rocks pre-planets. And, what are they going to tell us? These are quite literally the fossils of the solar system. And we have this opportunity now with Lucy as technology gets better and better and better, and we're capable of doing more. So our solar system is filled with these ancient remnants of planet formation. And I think we all know they're called asteroids. And, they tell a story. They're going to tell us a story. And that's why we're going out there is to figure out, to read the story. So it's kind of like a book, right? A book in all its pages, they're scattered all over the place. Okay, so now, Lucy is going to go out and it's going to find one page, and it's going to find another page. It's going to find another page. So, so we can rebuild that book on, how the solar system was formed, and hopefully, how Earth came to be. So they named the mission Lucy after the human ancestor that was found in Ethiopia back in 1874. And there's a whole story behind how she was named Lucy. The discovered Donald Johanson. They were elated, and there was a Beatles song on, Lucy in the Sky with Diamonds. And so that's partially how the name came to be. So I'm not going to focus a whole lot on the origin of the name of Lucy, but that was just one of the greater insights. I am going to relocate my bar because it's interfering with my thing. Okay. So the Trojan asteroids specifically, these are specifically the asteroids that share the same orbit with Jupiter. Okay, they're not the asteroid classes or families that are what we call the main belt, MBA. You're going to see the acronym MBA in the presentation. So those represent main belt asteroids. And of course, there's other types of asteroids out there that we're familiar with. Kuiper belt all the way out, and then closer to Earth, we have near Earth objects, NEOs, if you're familiar with those. But we're specifically talking about the Trojan asteroids that share the orbit with Jupiter. Now, I learned something recently that I thought was kind of neat, and I don't know where the origin of this came from, but if you're familiar with the story of the Trojan horse, comes out of some Greek, I don't want to say mythology, but it's a story about the Greeks fighting a war. And so I learned that the asteroids that are in the L4 point, and I'm going to talk about L4 range in a second, but the group of asteroids that are closer to the top of your screen, those are that's called the Greek camp, Greek as in Greece. And apparently the group of asteroids that are towards the lower of the screen, though that's called the Trojan camp. I just thought that was a fun little factoid that I learned recently, and I wanted to share with you guys. So we have a couple of videos. I'm going to try and get this next one coming up. My screen is frozen at the moment. Of course it is. All right. Okay, I think we kind of just covered this. But I did learn something actually in the audio that Ann was playing just before our conference call, and I hadn't heard of this before. So the ladies on the call, if you didn't hear it, were saying about how all these little green dots look really close together. But we have to remember how big space really is. Space in the universe is vastly huge. And if you're standing on one of these, you're not going to see the cluster like you see it in the video. These asteroids are approximately 9 million miles apart. And if you're familiar with astronomy and observing with a telescope or binoculars, they would look like a 10th magnitude star, and that's really faint. 10th magnitude star is a really, really faint star. So I actually learned something in the audio that Anna was playing up to. So if you hadn't heard that, I wanted to share it because it looks like they're really dense. You got to remember how big space is. They are really, really, really far apart. All right. So here comes our first video, and Lagrange point. Oh, sorry about that.
The Trojan asteroids are found in Lagrange points, which are these special places that lead or follow a planet in its orbit by 60 degrees. And it's sort of where the gravitational force of the planet and the gravitational force of the sun all cancel out. So if you put an object there, it will stay there for a long period of time, basically forever. So when we see objects there, these are objects that we know were in place a very long time ago. So if you just take a random asteroid and just put it in the outer solar system, the gravitational force of the 4 giant planets will just clear them out in a very short period of time. So they'll basically be gone. So the only places, it turns out, in the outer solar system where you can find stable regions are these Lagrange points. Lucy in particular is going to go after the Jupiter Trojans. We're trying to see a type of object that represents and constrains the formation of the outer planets. And you need to go to these Lagrange points in order to see that kind of object. One of the really groovy aspects of our mission is its trajectory, because we're visiting a record number of objects like these Trojans. And we do that with this very complicated dance, particularly in the beginning, where we are using the Earth actually as a gravitational slingshot. So Lucy will start off in an orbit very similar to the Earth, and then gravitational encounters with the Earth will actually pump it up so it gets out to the Lagrange points near Jupiter's orbit. So if you're going to understand how planets like the Earth formed, you have to understand how the bigger planets, which sort of dominated the whole process, came to be. And that's what Lucy is going to do.
Okay. Pretty cool explanation. So what are the Trojan asteroids going to teach us? So they're going to teach us a lot. What rocky and icy materials make up the giant planets. How and where did these planets form? And did they move around in the earlier solar system? There's a lot of background information not included in this talk that talks about the variability of a lot of these asteroids. And again, maybe in a future presentation, if you tell Ann you want me to do it, we can go a little bit more advanced into C-type and D-type and BP type of asteroids. So this is one of the great things about being able to visit so many at one time, is we're getting to see the variety, right? And they're kind of convinced that one of these asteroids isn't like the other. So what is it made of? Did it move in? Did it get captured? Was it formed there? So it's talking about early movement of these objects around the solar system. And again, if you're really into asteroids, you may know that they come in families. and they come in groups, and when they break apart, they come in subfamilies. So there's whole categories of asteroids. And they can kind of start piecing the puzzles together, and they can say, wow, this main asteroid, the main asteroid belt, but we're finding pieces of it all over the solar system based on spectra and spectrum. So it's really going to tell us, you know, hopefully about early movements in the solar system. And, you know, are these truly some of the materials that needed for life on Earth? You know, are we going to find, you know, water on them? Are we going to find organic molecules and matter? What are we going to find on all these? And so hopefully that's what's going to teach us. And of course, it's going to take a long time to analyze the region and the data. So I thought this was a little bit of fun. Lucy's going on a road trip, and so some of this is in English metrics and some of it's in metric kilometers. So if you're used to the miles per hour, 65 miles an hour, which I believe is about 100 kilometers an hour, and you can correct me if I'm wrong. So if we're just traveling on the road 100 kilometers an hour, it's going to take about 7,000 years to get there. And at its fastest, Lucy will be going about 40 kilometers an hour, but its average is going to be approximately 15 kilometers an hour. And when Lucy's actually passing the asteroid, they really expect it to have slowed down to like 3 to 5 kilometers an hour, and that's all due to the gravity, slingshot effects. So when it comes in close to the Earth, it's going to be speeding up. When it leaves Earth, it's going to be at its fastest. It gets farther and farther away, it's going to start slowing down until the sun's gravity starts making it turn its way back, and then it's going to start slowly speeding up again as it heads towards the sun. And it's going to be on this constant loop, right? So when it's nearing its gravitational source and leaving it, it's going to be at its fastest. And then when it's at its outer loop, when it's in the Trojan belt, it's going to, that little loop, it's going to slow down and slowly start to speed back up again. So it's gonna have some velocity in there for sure. So a little bit about the spacecraft itself. It's about 15 meters across, and Lucy right there in the middle. She's going to be about the size of a sports car, so she's big enough, certainly, and she's going to be unfolding. So this is Lucy in, you know, before liftoff. She's all hunkered in, ready to get on the top of a rocket. I don't have a whole lot of information about the rocket, but I can certainly get it to anybody that wants it, or you can go online and look up yourself. There's plenty of information out there. And here is one of the solar sails, totally unfurled. And this is going to be its main electrical power source. And one of the unique things about this mission is solar power. It's going to be its main electrical source. This is the farthest out into the solar system that anybody has ever sent a probe with its main source's power. Typically, when we send probes out, they have little thermal isotope engines, which are cleverly named. They're really just basically nuclear engines. Nobody really likes the word nuclear, so hey, it's a thermal isotope engine. There's a little bit more specific name, but basically it's radioactivity breaking down, and it's creating electricity. So we're going to be mostly solar on this one, all solar for its electric source. And here's a kind of a little quip with them testing the unfurling. So the mechanics are actually being done by the probe, and the sticks that you see up on the tube above it, they're just kind of being suspended there. They're helping you know, balance it out so we don't wreck the solar array. But here's Lucy getting its dry run, test run.
It's so pretty.
Yeah, that is kind of cool.
It's very pretty. But
That is
I
very
read
cool.
that they were having problems with the solar array. I hope the problem's fixed.
Yeah. So yeah, so what they've learned over the years with all the various missions that we're sending to deep space, and Hubble was a good example of, hey, Hubble was close enough so that we can fix it on our own, but we really need to develop future spacecraft so it can solve its own problems and we can kind of troubleshoot problems from Earth. So, Hubble taught us a lot about, what we can do and what we can't do. And not to get off topic, but we have large arrays out there. Spitzer telescope, for example, it's following Earth, and the Spitzer telescope is a huge laboratory, and it's got some incredible findings for us, but it's never going to be serviceable. So we have to start equipping our spacecraft with some self-ingenuity, and unfortunately, with AI, artificial intelligence, these spacecraft are getting better and better at fixing their own problems. So, but I agree with you. I have not heard an update whether or not they solved the problem, but double finger cross, I'm sure they're going to get to it. So I agree with you 100%. All right. So this just talking about perspective a little bit. We've had some missions to other asteroids or minor planets, and this slide does not talk to any of the asteroids we're going to be visiting. These are past ones. So you have to think about, we're going to visit 8 asteroids on this mission. 1 is on our way out, and then 7 are going to be in the target zone, the Trojans. And when you think about it, we've explored 8 asteroids before, but they've all been on different missions. This is going to be like the first mission where you're going to do multiple asteroids all at once. So if you think about cost savings and technology and development, that's just a huge advancement. The only probe that we've sent out or spacecraft before actually visited 2 minor planets or asteroids, and the 2 big ones right here. The Dawn mission many years ago visited Vesta first and orbited for a while, and then it left Vesta and is still in orbit around Ceres. So that was a big deal then, right? Because all our missions are targeting one object in space, and usually it's a flyby. It's not something where we stop and go into orbit, or even a lander, right? Some planets we've done landers. So Dawn was a really, really big deal because we visited 2, and now we're going to visit 8 all in one. And so it's a really big deal. It's a really big advancement, and I just really hope they keep as we say in America, upping the ante, meaning, keep challenging, keep moving forward. So next time it'll be 20, and the time after that will be 50, and the time after that will be 200. So, this is really exciting times in the history of space exploration. We're just in the infant phase of it all. I mean, we're before infancy. It's like we're kind of like pre-toddler. We're not even at kindergarten yet. So those of you who are listening, especially if you're young, the technology for space is exploding. And when I was your age, we won't say how old I am. I'm old enough. Probably a lot of you are my grandkids. Back when I was growing up, you had like one new astronomical discovery every 6 months, and there was just, 2 main space companies, and it was Russia and the United States competing. And now as Anne can attest, we're on social platforms like LinkedIn, and there are just space companies popping up everywhere every day. So it's really an exploding industry. And if any of you want a future, plan a future, now is the time, because by the time you're ready to get into it, we might be at the kindergarten phase of space exploration. So now it's just an exciting time to be in it. So I wanted to share, some perspective. We used to do one 10 years, and then we started doing one every 2 years, And then we say, hey, let's do 2 bodies. And now we're doing 8 bodies. So it's really cool. So these are the targets. And I won't spend too much time on these, but again, they might form questions. Feel free to take a screenshot, take out your camera, take a shot of this, and go explore on your own. So the first one, so off to the left, you see an L4 and L5, kind of small and red. Those are the Lagrange points. Okay, remember the video? There's 5 points that are stable in space. Pretty much for any planet. Earth has 5 Lagrange points. Venus does, Mars does, the sun does. So to give an example, Earth in its Lagrange points, Lagrange point 2, which is beyond the moon, so it's kind of headed outwards towards the solar system. That's where they're going to plant the James Webb Telescope that is scheduled to launch here in a couple of months. The James Webb Telescope is the replacer for the Hubble Space Telescope. But you have to remember, Hubble was repairable. It's in Earth orbit. The James Webb is going to be way out there. It's not going to be serviceable. It don't work. It doesn't work. And even Earth has a few asteroids of its own sharing its orbit. And again, it's at that Lagrange point 4, Lagrange point 5. They're small asteroids. They're stable. They're never going to go anywhere. But coming back to these, in the top, you have the L4, Eurybates and Keita. Now, Keita is a very small moon. I don't know if you can see that little small thing right at the top. And that was actually a new discovery very recently, that Eurybates has a moon. And in fact, they're finding a lot of asteroids have moons. This is nothing unusual. And it's going to be really exciting to get out there and see what everybody's made of. And then Ptolemy, so 2027, Lucas 2028, Horus 2028. And then we're going to have a break. And then Lucy's going to, it's going to do that gravitational loop. That's going to come back in around Earth. And it's going to flip around Earth, go back out. And by the time it gets back out there, we're going to have this binary asteroid where it has literally a center of gravity. And you can kind of see that little video artist concept right down there. So very exciting. So kind of going back to what I said, L4 apparently is named the Greek camp. So, and then the L5s are the Trojan camp. And I'm still fascinated to find out kind of how they determine that, who was betting who on that game day. I'm not really sure. So let's do another quick video.
So to steer a spacecraft from millions of miles away, we have to first track its trajectory. So we have to determine where in the solar system the spacecraft is, predict where it's heading, and compare that to where we want it to go. So the navigation team ensures Lucy's on the right trajectory by tracking Lucy's position and velocity in the solar system, predicting where it's headed, and adjusting its course so that it aces the flyby. So once Lucy starts approaching one of its asteroid targets, the navigation team utilizes the instruments, the cameras on board, to take pictures of the asteroid and background stars, and that helps us hone in on targeting this close flyby. So commands travel at the speed of light, and over the course of Lucy's trajectory, its position from Earth is varying substantially. When Lucy is near Earth during our Earth gravity assists, it takes a mere seconds for the data or commands to be received by the spacecraft and for the spacecraft to send data back to us. But at the farthest extent of Lucy's trajectory and the farthest distance from Earth, it can take up to an hour for our commands to be received traveling at the speed of light. It's not only the data encoded in the signals, but it's the properties of the signals itself. We know what time the spacecraft sent the data, and we know what time it was received on Earth. So we can calculate how long it took the signal to travel at the speed of light, and that gives us information about how far Lucy is from Earth. And then we also can get velocity information because the spacecraft is moving away from the Earth as it's sending those signals, and so there's a change in the frequency of the radio signal, and that gives us information about velocity. So like all NASA missions, Lucy is designed to be robust to anomalies or surprises. But in the event that something unexpected happens, there's either a contingency plan on the shelf or a group of relevant mission experts are brought in to come up with the best solution to solve the problem.
Excellent. And all these videos that you're going to see, I believe there's only 4 videos. We've done 2 of them. All these videos are available either on YouTube or on NASA's Lucy mission site. I was telling Ann before, I think there's a total of 20 of them, and you know, all just very, very informative. So and all the videos that I'm showing are absolutely 100% available online. I would just go, you know, whatever search engine, you know, NASA Lucy mission, etc. But don't do it now. Don't get distracted. Got more to go. So this is actually one of the most important slides, and you know, mostly for me it's the interiors, but let's start with surface geology, right? So we're going to be taking cameras. We got a big camera up there. It's called LORRI, long range reconnaissance, and it's very similar to other cameras that we've used on other missions, including Mars right now. We have a LORRI, earlier version of LORRI, the Mars Reconnaissance Orbiter right now, and that one around Mars is the largest camera ever to go beyond Earth's orbit. And you know, it's in Mars orbit. It can take photos of, you know, something to the size of a coffee table down on the surface. So Lucy's got one, and it's even a little bit more advanced than the one that's on Mars. So really looking forward to the surface geology. And then there's another instrument we're going to talk about in a minute. It's really just a thermometer, and you know, this is really technology that's really advanced, and some of you may be familiar with this technology. You know, with the pandemic and COVID, you know, now there's like cameras in buildings that are taking your temperatures. You walk in the building or through the airport. I know my company has one where I work. It's quite incredible technology. My workplace has a thermal camera that can read 30 people all at once, you know, so it's amazing technology. So now we can do that with planets, right? And we can just kind of, you know, take the temperature of various areas. And that really leads into the next one, where it's interiors. We have sent many missions to the asteroids. We've sent impactors, we've watched the dust, we've taken samples, we have sample return missions, and we have really kind of observed a whole spectrum, right? And you know, these are kind of the major ones. Is it a very solid object? You know, is it a core? You know, and then it might have major fractures, right? Because of all the bumping and grinding that occasionally goes on. And so it may be solid, but you know, it may be kind of porous, right? There's big cracks because it's been bumped a few more times. And then we talk about the true nature of gravity, right? Just, you know, gravitational, larger objects tend to come together. And while it may look like an asteroid, it may look solid from the outside, from the inside, it may be just a group of larger rocks put together, but because, you know, time, billions of years, it's attracted dust. And from the outside, it may look like an asteroid, but the inside, it may be just a loose rubble pile. They have found that. And then the fourth major category is kind of a mixture between both. It's just kind of gravel. It's all small stuff, and it's nothing extremely large. And again, gravitationally, electrostatic. These items are just kind of clumping together over time, and they kind of just keep sweeping the solar system. And stuff comes in from the Kuiper Belt, stuff goes out. You got comets leaving debris, comet trails. So they're just kind of sweeping up the solar system. Kind of being, the lobsters of the ocean. It's going around the bottom, just kind of taking everything up. And then the other thing too is satellites and rings. The one that you're seeing right here, that's Ida, the larger asteroid here on the lower right, and its moon. And this is actually asteroid we landed on. This was a NASA experiment many years ago where they were practicing with photon engines. So this wasn't solar, it wasn't nuclear, it wasn't anything, it was a photon engine. And it was a very successful mission, taught us a lot, but they actually just nestled this little spacecraft right on the surface of the asteroid, and it kind of just ran out of energy, and it's still sitting there. And I believe that little moonlet's name is Dactyl. I could be wrong. I didn't Dactyl. But again, another asteroid with a moon. So this is actually fairly common out in the asteroids. I believe this is going to be the last video. And I believe here we're going to start introducing you to some of the instrumentation, and we'll talk for a few minutes about that.
Nope, Lucy. Still a little way to go before you get to your first Trojan asteroid. But it looks like you're coming up to the main belt asteroid, Donald Johanson. Right, this'll give you a chance to check in on your instrumentation before you get out to the Trojans. This first instrument is called LaRalph. It will take color images of the Trojan asteroids using visible and infrared light, helping scientists map craters and mountains and figure out what the asteroids are made out of. Next, this is LLORI, the Long-Range Reconnaissance Imager. This camera will provide the most detailed images of the surfaces of the Trojan asteroids to help scientists figure out what's been happening since our solar system formed. This is LTES, the Thermal Emission Spectrometer. Basically a touchless thermometer. It will measure the temperatures on the Trojan asteroid's surfaces to tell scientists whether the surfaces are rocky or dusty. Lastly, you couldn't get the job done without your tracking cameras or the T2 cams to make sure the asteroids are always in view. And the high-gain antenna that lets you communicate with Earth. The scientists back at home will use your radio signals to measure the mass of each asteroid as you fly past it. Right, Lucy, how could I forget? You also have 2 huge solar panels to give you electrical power as you fly out to the Trojan asteroids. Farther from the sun than any previous solar-powered mission. Just a bit longer now before you get to your first target. Rest up and get ready to put all of those instruments to good use. I'll check back in with you once you make it out to your first Trojan asteroid.
Excellent. So from my perspective, actually, there's not a whole lot of instrumentation on this spacecraft. To be honest with you, I'm used to, spacecraft with a lot more instruments. New Horizons, who went past Pluto here a few years ago, was one of them. There were so many instruments, the thrusters actually had time. All right, I need to move this way. I need to move up. I need to do that. I need to give this instrument, its time. And then I got to flip myself over to give that instrument its due time. So, I believe New Horizons had like 8 instruments. It's just a lot. But we also got a lot of good information out of it too. So I consider this mission a fairly simple one, which is nice and refreshing. It means we're kind of, we're doing a lot with a little. And you're going to see that that's kind of the way to the future. So again, we're going to touch on it real quickly. LLORI is the long range reconnaissance imager. the TT cam, also called T2 cam, and those are your tracking camera, right? Its sole focus is to make sure that, you know, we are targeting in on our target. That's its sole focus. Radio science, that's just talking about, you know, the dish, how we're going to get back. The telecommunications link with DSN. DSN stands for Deep Space Network. And that could be a whole new presentation just on itself. The DSN network is an absolutely fascinating program. It basically is the global link, meaning that any spacecraft in any direction can constantly stay in touch with Earth, especially NASA. You know, we have our Goldstone, there's the California, and then there's the Australia facility, Canary Islands, which is in the Atlantic. So the Deep Space Network is just a huge global connected set of very large communication devices, receivers, and antenna. Deeply fascinated. I highly suggest looking at Deep Space Network if you really want to see how all the different pieces go together, and you know, everything that we've got going on in the outer solar system, and Jupiter and Saturn, and now the Trojan asteroids and Venus and Mars. They all communicate back through the Deep Space Network, DSN. So fascinating reading, lots of books written about it, fascinating history, early pioneering in radio astronomy. Highly recommend follow up on him with that. LaRalph is also, like Lori, is kind of, we're being consistent now, right? So we early probes, the Voyager, you know, Galileo, and a lot of the others, we sent off the Mariner and Viking. Each spacecraft, we're inventing something new, right? So now we're getting to a point where we're like, okay, we like these instruments. Let's just keep going and bettering what we've done. So Lori and Ralph are examples of those. They've been used on previous missions. They've just been upgraded and reconfigured for these missions. So personally, since, you know, following spacecraft for the last 30, 40 years, and I won't say any more than that, you know, this is kind of really good. So this is like an evolution, right? An evolution of technology, an evolution of learning. And we're saying, hey, we finally found something that we like, and we're going to start using it over and over and over again. So that tells me we're coming to some standardization, and we're coming to, you know, things we can kind of reuse, right? Because how many times do we do a prototype and, you know, it all sits in a closet, and now we're starting to reuse it. And then at the bottom we have the tests, and again, that's the thermometer that's taking temperature. Going to take a slide and talk about each one. So something I learned a few years ago, and it's one of those things where you're like, you assumed, but you shouldn't have assumed, and like, you know, I was almost mad, to be honest with you, and I was mad because, you know, here I was thinking that, you know, we've been studying the planets, studying the stars and the moons for decades and decades, and a couple of cases, centuries. And we launched New Horizons, which went to Pluto many years ago. Went to Pluto actually recently, but it took a long time to get out there. And a very interesting thing I learned, and I read that they're doing kind of the same thing here. So I was listening to a podcast and talking about Pluto, and the mission project managers were like, well, we don't really know where Pluto is. And I stopped and I'm like, well, what do you mean you don't know? You launched the probe. What do you mean you don't know where Pluto is? And they said it very simply. And I was mad, and it was a revelation at the same time. They said, well, Pluto's got an orbit of 250 years, but we only discovered it 80 years ago. It's only done a partial arc. We've never tracked Pluto for its entire orbit. we're guessing where Pluto is. And, that's that point I was like, oh my God, you telling me we really don't know where Pluto is? But of course we do. We just don't know to a pinpoint. And so the same thing here is we have ground-based telescopes for the Trojan asteroids, and they're mostly accurate. They're accurate enough so we say, okay, we figured it out, we can do this mission. And what's not very public is they're going to use the Hubble telescope over these next 3 or 4 years to use occultations of the asteroids to stars to get even more precise locations. So while Lucy's already been launched and it's going to spend 2 or 3 years getting to where it needs to go, Hubble is actually going to start taking more accurate details for the locations for this. So Hubble is going to be very accurate for the asteroid location. And that's what the TT cam is, those little set of eyes. They're always going to be focused on the target. And that's going to get you your precise flyby. And that's basically the sole purpose of the T2 cam is it's going to take the information that we've learned from ground-based and take the information we've learned from Hubble, and then it's just going to focus. And, if you're driving really, really fast and you're going to try and like skim a pole, something, many, many kilometers down the road, you need to be laser focused as you drive really, really fast down the highway, don't you? You can't be looking around and sightseeing. So that's kind of the analogy. It's just like, okay, so you're going to drive a long distance on the highway and you're going to try and basically, go past a tree and miss it by, 2 centimeters. But the tree's 1,000 kilometers down the road. So the ground base kind of gets you there. Hubble gets you mostly there. But the T2 cam, as you approach that tree with your car, you want to miss it by 2 centimeters, that's its sole function. Lori, again, black and white cameras. This is an example of what Lori sent back to us. This is Pluto's moon, Chiron, and it's basically going to show us, very detailed geologic features, and hopefully even more clear than what we see here. So the Ralph is actually 2 instruments in one. The first instrument is going to be the color camera. And so this is an example of the color camera of an asteroid after it passed Pluto. So New Horizons, many years ago, flew past Pluto, discovered a ton of stuff. And so now we're going to start targeting New Horizons to other stuff and Kuiper Belt as it flies out. So this is something, a flyby with color camera. This is a Kuiper Belt object that you're looking at on the screen, and this is way beyond Pluto. But this is an example of what we can capture. And we talked about earlier about types of asteroids. Whether it be solid with crack, could be gravelly, just could be lumped together by gravitational. And that's kind of what we think we got here. We think we've got kind of 2 asteroids kind of attached at the hip. And all that bright ring that you see that's kind of attached into. And that's just dust that's collected there over billions of years. And so, who knows what we're going to find out. And also they're going to be able to tell us if these things are geologically active. We're assuming they're not active, but we assume Pluto wasn't active either, and that really blew our socks off. And again, the other instrument that the Ralph has, like I said, it's kind of got 2 things. It's going to be an infrared spectrometer. And really, this is going to help us find the fingerprints of silicates, ices, and organics. I mean, what if we find organics on these asteroids? And that could really shake up the entire way we thought life came to be on Earth. Maybe life didn't start on Earth. Maybe it started on some other planet or asteroid. I like to remind people that our sun is not a 1st generation sun. Our sun, the dwarf star, is a 3rd generation star. So it's gone through a couple kind of recycling itself. Initially 1st generation star, hydrogen, helium, blew itself up, created some more materials, formed another star, it blew up, condensed into a third star with even more heavy metals. So maybe life started on that second generation star. We don't really know. It's all speculation. So, I mean, what if we find organics, on Europa and Enceladus and even Mars and, on these asteroids? It's really would change the way we think about us and our place in the universe. So it's going to be really exciting to see what we find. Again, the thermometer, really, obviously, the sun side is going to be warmer than the backside. Some of these Trojans rotate at different speeds. And again, it's going to help us tell us, hey, is it a solid? Is it a rubble? Because obviously, if it's a rubble, it's probably not going to have a even temperature across. You're going to see something that may look like more Swiss cheese. This is an example of what Lattès did with the OSIRIS-REx mission, which is an active mission. Please feel free to go out and research OSIRIS-REx. It's bringing back a sample return. It's still on its way back. It's an active mission, and on that mission, it was called OTES. On this mission, the similar instruments called TES, Lattès. Obviously, the TES is the same. So if you look at LTES and OTES, so one's Lucy for the L, and the O is for Osiris. Basically, it's taking its temperature. So those are the 5 main instruments. So we're getting towards the conclusion. I've kind of got 2 versions of this kind of flyby animation. Couldn't decide what to go with. So I was like, you know what? We'll just do them both and they'll be really quick. So again, I'm not going to read everything. We are launching from Earth. And so just a fun fact, Jupiter is actually going to be closest to us when we actually launch. It doesn't really mean much, but hey, it was fun. So it's going to launch and it's going to do a double loop, coming back around. And we talked about the main belt asteroid named after Donald Johanson, the person who discovered the Lucy early human fossils. And that's in the main asteroid belt, and that's going to be in 2025. Okay, so as you watch the animation, so here's going to be our first visit, and they believe that, they're really interested about this one because they really think that this is the asteroid that doesn't belong with the rest of the Trojan asteroids. So this is really going to be the curious one, right? And they're pretty sure that this was the survivor of a massive collision. And they've got techniques about how they've determined that. And again, that could be a whole other presentation. And I'm filling up your pipeline for you. That'll be in 2027. But I want you to kind of see how this starts to loop around. And now it's the sun's gravity is starting to take over. It's slowing down. Yep, here's the little moon. So here's Hubble. Kind of right there, that little green circle popping out. That's the moon, Keita. Really tiny, but we're gonna hopefully explore that too. Oh, I did have one more minute. Last video. We are in the final stretch. You can hang out with me, that'd be awesome.
There's still 5 more Trojan asteroids to explore on your 12-year journey. Each one has a different story to tell about the history of our solar system. Next up is Polymele, a mere 21 kilometers or 13 miles in diameter. Afterwards, you'll be zooming by Lucas, which rotates at an extremely slow rate, with each day being about 18.5 Earth days long. Afterwards, you'll be on to Oris, which might be rich in organics and carbon. Lastly, you'll be on your way to a twin pair of asteroids, Patroclus and Menecius. These asteroids, relatively unchanged over 4 billion years, will give us a glimpse of our solar system's distant past. With each flyby of a Trojan asteroid, you'll be looking at time capsules from the birth of our solar system over 4 billion years ago. Lucy, What your observations tell us about the composition and properties of the Trojan asteroids could give us clues about how Earth came to be. Absolutely. Carry on your journey, Lucy. And don't forget to call and show us what you find out there.
Okay. Home stretch here for the presentation. Again, we kind of covered this in the video. The next one is Polymere going around. So you kind of see the slowness. Lucy's not going on. Lucius, 2028. She's starting to come back in. Horus, 2028. Speeding up, getting that down to that 40 kilometers a second. Going back out. So really interesting here. So you notice how Jupiter has been going around in the circle. So while the probe Lucy is just going to do the same loop, they figured out a repetitive orbit. So Lucy is going to be in the same orbit, but it's going to be catching the Trojan asteroids at different periods in the orbit. And it was just really genius part. And this is just a graphic more than anything else. So one thing I would really want to point out here as we get close. All right, so on the left side is going to be the sun. And you can see the shield, little triangular part, that's the communication disk. So the solar array and the disk is always going to be facing the sun and Earth. And on the right side is all your instrumentation, whether it be you call it the front side or the back side, it doesn't really matter of your opinion. And so when it's cruising, your spacecraft and the communications array with the solar is pretty much always going to be facing on the inside, and they really want to try to go on the inside orbit of these asteroids. Okay, it's gonna stop here in a second. All right, so we're gonna do this one more time quickly, a little different here. Okay, so it gets its first gravity assist. It's going around basically the equator of the Earth. It's going out. It's gonna come back for its second slingshot. Going out, there's Donald Johanson. Now on this graphic, on this yellow box, if you look down the bottom, it's really small, it's hard to see. It says 50 kilometers. That's just a scale, okay? And again, the MBA rehearsal in blue, main belt asteroid. So it's going out. It's gonna visit its 2 or 3 objects here, or it's 5 actually. Oh, sorry, so Lagrange L4 point. Okay, P-type asteroid. It looks to be about 15 kilometers across. And then it's going to circle in. Lucius, a D-type asteroid. Kind of looks like a peanut. And again, we're getting bigger. It looks to be, what, about 30 kilometers across, maybe? Circling back in, it's going to hit Horus. We're getting bigger. That probably is 50, maybe a little bigger than 50, a D-type asteroid. And so now, again, watch Jupiter, the green circle at the bottom. Now, this is very interesting. And the twin binary asteroid, it turns out they're about 22 degrees off the ecliptic. So basically, you have a plane of the solar system. These binary asteroids, they kind of not only spin around each other, they kind of spin around the orbit of Jupiter in the same place, but they go above the plane, below the plane, above the plane, below the plane. So they worked it out so that when Lucy comes back, it's kind of got to go over the North Pole so it can get that 22 degree angle. All right, and then at L5, Lagrange 5, you got a pair of P-type binaries, and then kind of just keeps going. All right. And really, I've come to kind of the conclusion. So with this, the fascinating thing is the mission is 12 years and 8 asteroids. And, what we said is the mission. However, there's nothing to say that Lucy couldn't keep going for decades, hundreds of years. She's just going to be out there. She's solar powered, and she could just keep going. She does have a little fuel on board, so I'm presuming most of the 80% of the fuel is going to be used up in its primary mission. But as far as an extended secondary mission, Lucy's just going to keep traveling through the inner solar system. And I'm sure they're going to try their best to use her for the years and decades to come. And kind of wrapping it up, if you guys want to become more involved, again, you can take a computer screenshot of this, or Anne has this information. I can get this to Anne. Take your phone out, take a phone of the screen. They're going to need program managers, and they're going to need people for years to come. This is a 12-year mission, and the people that are working on the mission right now are probably going to be retired before the mission ends. So they're really thinking ahead and trying to get other people involved. So I haven't read anything where this is limited to like American students or anything like that. Look into it, see what it's all about. This may be something, if not for this, something else for your futures, or just to stay in touch with. All right, I'm going to pop the screen to the very last one. And these are mission resources. Again, you got a couple of websites there. There's a Twitter, there's a Facebook, there's an Instagram places. So I'm going to kind of leave this up on the screen for a few more seconds for people to capture the information as you wish. But that's it from my end. I hope everybody got something out of it. I know we're going to have a Q&A. I literally have all night. It's midnight for me. I literally do not have anything to do for the next 6 hours. But I know everybody else has things they got to do. So, Anne, I'm going to kind of turn this back to you, and I'm going to kind of take the presentation off the screen and stop sharing, and I'll let you kind of manage it from here out.
Thank you so much, Todd. It was really, really a good mission overview, and I'm sure some of the physics probably still too complex for the young
Sure.
audience, but that's why you all need to write it down, all of the physics terminology and concepts that you don't understand, and you can start learning about it, because if as you go on, then you will need to understand these things for future missions as well. And you learn it in the grade 12, more on astrophysics. So I think it's fascinating. And a new horizon, the space, the flyby as well. That was how many years ago? They took the first image of Pluto. That was
I believe the flyby was actually, I could be wrong, but it's 2017.
Yeah. I remember it because I met the guys in 2014, and then I was like, oh wow, still that's also a very long mission, It's also like
Absolutely
9 years to get there as well. And then I think and also with the like old instruments, but they're able to capture, right? So you can just imagine
Absolutely.
for our future mission, as we improve our cameras and sensors, it's just becoming very more advanced, and we have better images, and we just need to solve the internet in space problem. But
yeah, and they're planning on solving that too. They're actually talking about setting up subspace connections as you further go out, and who knows by the time some of the viewers will do that. So Ann, you and I never talked about this, but I'd like to add this for your team there is my only education in actual astronomy was I took a freshman college course when I was in 8th grade, and it was a summer course. So I actually never took a college astronomy course. And everything I've done and do is all self-taught. I am a self-learned astronomer. And, even if you decide not to go to college and study astrophysics or all this kind of stuff, I taught everything myself. I learned everything myself because I had the interest. And as I got older, I realized that I was more advanced in the topic than my peers. And so, I heard about this volunteer program at NASA 14 years ago. And I said, hey, I love to talk. I love to go out there and educate. Can I be part of your program? So I applied and they accepted me. And even though I do not have a formal education in physics or advanced mathematics or chemistry or anything, you can be self-taught, you can learn, you can engage, you can go out and promote, be an advocate. And right now the world is open to anybody in the space industry, and it's just growing very, very rapidly. So you don't need to go to study astrophysics to be involved in space.
Yeah, I absolutely agree. And you don't always have to also be from a science background nowadays, from the arts background as well. We need it, right?
Absolutely.
For space farming, space architects.
Absolutely.
Like we need visualization on how we're going to settle the first human settlement on the moon and Mars, how we're going to design the habitat and, so like the city. And that's all a lot of arts background as well. And self-learning is definitely sort of probably the fundamental skills that you need to have in any industry, but especially in space industry, because I think there's always something new, and there's so much information that's available online already. And then there's always something new as well from the missions. And we have to sort of learn as well by ourselves, and all the self-motivation, so we can upgrade our knowledge and upgrade our skills. And that's why we offer this kind of sessions as well for public. And there's a few people already that's joining us today, and that's very good. that's what it's for. And for the internet and space, actually, that will our colleague in Singapore is they're also a startup company, and they're planning to have they're working on the laser space communication in space. So it doesn't have to be intermittent connection to relay the data to Earth and also in space. And with the growing plans of commercial space stations, that's going to be needed even more. So that's fascinating as well.
Yeah, no, again, you don't need to be the smartest person. Astronauts are not necessarily the smartest people.
Don't say that.
No, I mean, you have to,
I can't be an astronaut, man. I don't think so.
So you have to be able to think quick on your feet. You have to be innovative. If there's a fire, you can't panic. So you have to be, you have to be smart enough to be able to survive on your own, and to be think quick on your feet. If something happens in an emergency, you got to be calm, collected. Got to be used to tight spaces sometimes. And if you go on spacewalks, don't have a fear of heights. So it's a lot of things, and it takes all types of people to really engage. And to your point, Anne, astrobiology, that's a real science. It's been a real science for 20, 30 years. Agriculture. I mean, people are really studying agriculture in space.
Actually, the other
and-
day, yesterday, there was a briefing by also Houston Spaceport for the
Sure.
and Johnson, and the number one job on the list for future is space farmer. So
Yeah.
yeah, I mean, we need to eat if we ever go back. You know, if we ever plan to settle in space, then we need to grow food, and yeah, space farming. So kids start thinking about a career and as a space farmer.
Yeah, I mean, seriously, they're honestly thinking about, settling on Mars. How do you use the Martian soil and resources, to grow your vegetables and your fruits? And do you need to actually start mining local asteroids for those minerals, ingredients, and calcium and everything else that you can't find on Mars? So then you got, mining involved in there. And so it just keeps growing, right? It's kind of like early merchants on Earth, early trading with the sailing ships and the over mountain routes. You got to think about Mars and asteroids. It's the same thing. The instead of the ocean, instead of sailing the ocean, now you're sailing in space, and you need to find the resources. And if you got to go to a local asteroid and dig a little ditch to get your resources, then that's what you do to bring it home to Mars and grow your vegetables.
I still think it's easier to land on a planet or on the moon rather than an asteroid and trying to live there. It's not going to be a nice climate. But let's throw the questions to the floor. I mean, we have a few enthusiasts here. Titan, Bayan, Jaliza, Tala, did you want to ask any questions? Ahmad and Fatih. Tala has raised her hand, so she really, really wants to pursue a career and first study and then career in the space industry. So she's already
That's
wearing
awesome.
a helmet.
I like that. That's awesome.
Sure, Tala, what did you want to ask?
In the Google Forms, I saw a question about a telescope. So is there some kind of online site we can check out?
Telescope. Oh,
Are you talking about a specific type of telescope or just in general for your everyday use?
Uh,
in which Google form? You mean the registration for the webinar?
yeah.
Oh, okay. Because I asked, has people seen moon or any planets from a telescope, and did people
Okay, yeah.
see from a public telescope? So we will have some telescopes in Bali next year, and we'll announce it. So when we do our space camps here, you can come, or even for a weekend, get your parents to come and take
Yeah,
you here.
no, that sounds great. No, I do own a telescope, but I'll be honest with you, I really don't take it out as much as I thought I would. In my time, I've volunteered at 2 different observatories, an observatory in Connecticut, not terribly far from here. I lived in Texas for 10 years in Houston. I have a volunteer manager at an observatory down there too. So, again, if as you grow older and there are opportunities, volunteer at some of these organizations and, just get people engaged and, find a group, create a group in a few years, create the group, and have star parties. I've created several star parties. It's just a matter of sometimes not looking for a place to go, it's creating the place to go. And I think that's kind of been my thing, is like, anything over here? Nah. Anything over here? Nah. I'm going to create it right here. And that's the attitude. That's just kind of the way I've always approached things. And I didn't take an astronomy course, and I didn't take a course on telescopes. I said, all right, I want to figure it out. Let's do it. And there's a saying, became famous in a movie, but there's a saying, keep moving forward. That's all you got to do. Keep moving forward. Sometimes you got to take a step back, but keep moving forward. If you have an interest in telescopes, make your own. You can do that.
Yeah.
I
Yeah,
have a
we don't have many public observatory at the moment here. There's one in Bandung and Lembang, but so hopefully we have some next year here. We will announce it soon. So next, Jaliza, how do I pronounce your name?
It's Jeliza.
Jaliza. Okay. Hi, nice to meet you.
Nice to meet you too. May I ask for advice on how to, on ways on to teach yourself more about astrophysics or astronomy? Because so far I'm also trying to do the same thing, but I can't really find like a really like good sources for such topics. So I want to know if there are other ways to be teaching myself more about astrophysics and the likes.
You know, so I'll tell you how I really got my interest. And I'm kind of gonna answer your question, but it's gonna be kind of my own personal story. I was inspired, and that's truly what it was. And so for me, developing my love for astronomy and space and physics and all that it started from a personal level, a human level. And for me, growing up, that was a television series that was out there, and you can find this on any of your search engines likely. And for me, that was the series was called Cosmos with a C, and Carl Sagan was my big inspiring. But what I loved about it was how inspirational people were throughout history. So what I would suggest is start simple. Just start simple and fall in love with it. I realized when I got older, I wasn't really as good in advanced math as I had hoped I would be, but I loved it up to a level. So for an example, I would search, if you haven't already, 3 laws of planetary motion. Start simple. That is real simple math. It's fairly easy to understand, and just grow from there. I would learn from early astronomers, Copernicus, Huygens, Tycho Brahe. These are all the early European astronomers that really set the foundation for the Jovian moons, for example. So kind of learn the basics, learn about the founders, make it personal, and realize how they discovered the solar system with very simple tools. And I started simple, and it really started with the 3 laws of planetary motion. And then I just grew from there. I'd get a little bit more advanced, I'd do more techniques. And for me personally, I got to a point where I was like, okay, that's enough math for me. That's enough math. And I wanted to make sure for me personally that I didn't lose interest in space and astronomy. So, I had grown up thinking, I want to be an astrophysicist. I'm going to do all this and everything. And when I got to my senior year in high school, and I was getting into the advanced math, I really realized this may not be what I want to do. So I made the personal choice of keeping space and astronomy as a hobby, a special interest. But my suggestion for you is finding resources. I think a lot of the resources you're going to find either not specific enough for you, or it's too advanced. So I would start really simple. And again, 3 laws of planetary motion. Learn about those. It's advanced math for your age, but I think you can handle it. It's fairly simple. And look up Cosmos. And maybe you'll find the same inspiration I did. and really make it personal and really understand why things are and how they came to be back at that time. You know, Giovanni, like I said, there's Kepler. A lot of these missions that are named after some of these original people. Galileo is another one. These are people that lived 300-400 years ago, and they figured it out very simply. If you can kind of understand their early math, I think you'll fall in love with it, and you're not going to let it go. So find something you can fall in love with and just let it take over. But find something at your level for sure.
And also Jeliza, actually, one of my mentor from Bandung Institute of Technology, Pak Chatif Kunjaya, he actually wrote a guidebook for students, high school students, to prepare for the astronomy Olympiad. So definitely astrophysics is included in that book, and you can order. I will share the information in the WhatsApp group. If you're in the space education WhatsApp group, I can share the information there, and you can order. It's about 125,000, I think. And we are in the middle of translating that to English, so it can be available for students worldwide as well. But Astronomy Olympiad is a global competition, and it's actually compulsory for all schools in Indonesia. The students can join when they're in grade 12. But that's like sort of, you know, preparing the students for the Olympiad, and lots of exercises, and it teaches a variety of the astrophysics, you know, like formulas and theories. So you can share that about the book as well.
Yeah, I'd like to kind of add something onto that, and I think sometimes this gets lost when we talk about space and astronomy, right? And I think, Anne, you're going to figure out where I'm going with this. Is you don't need to be good in math to be good in space and astronomy. Okay, there are so many fields exploding in the field of astronomy. It's like medicine, right? People specialize in the nose, people specialize in the foot, people specialize in the heart. There are so many branches of astronomy now. It's amazing. It's mind-boggling. You can just specialize in parts of cosmology and deep space objects or planetoids. People spend their entire careers now focused on just little areas. And like I said, you don't need advanced math for a lot of these areas. You know, there's radio astronomy, and there's other types of stuff. And like I said, there's cosmology, there's deep space, you know, dark matter theory. That would be pretty advanced, but you don't always, I guess what I'm trying to say is you don't always need to be really, really good at math to be successful in space and or astronomy. There are so many branches now, you know, and Anne alluded to earlier, you know, biology, project management is a big one. And just, you know, people need, Mars is going to need a librarian. I mean, seriously, Mars is going to need cooks, right? You know, you're not going to build a McDonald's on Mars, right? Not initially, but you know, people need to eat, and they're going to need to be support people. So there's so many branches of astronomy right now. You know, don't force yourself into unhappiness trying to learn the math. Math is going to be important for sure. I'm not going to say it's not. But if you realize one day that, you know, calculus, it's not for me, wasn't for me. You don't beat yourself up. There's plenty of room in space and astronomy in the future for absolutely everybody. And had alluded to communications, big need in the future for communications. So like I said, don't get so hung up on the word physics. Very lofty goal. I highly suggest you strive for it, but at some point, if you really realize that advanced math is not for you, don't worry about it. It's fine. You can still get into education or a whole other slew of areas. So I think that's my really big thing for everybody is we're not all great at everything. I'm good in math. I'm just not good at advanced math. and I stopped before it made me miserable, and before I started hating astronomy in space. As you can see, I've been a volunteer for NASA for 14 years now. I'm not great in advanced math. I found another way to be involved. So that's just my other thought.
But if you like it, of course, and if you're good at it, and everything is so much easier in high school, I tell you, I've been there. Go for it, you know. And that's one of my
Absolutely.
I did physics until in high school, and then I was going to continue to aerospace, and then aerospace engineering, and then I'm like, maybe not, you know, I'll do something else. So so I did not. I really wanted to do aerospace engineering, but there's many ways to go to the space industry, and that's another session on its own that I can share to you. But Ahmad, I think you raised your hand, and then we go to Vian, and I think we can close the session. Ahmad, what did you want to ask?
Yeah, actually, I have a few questions, but before that, sorry for my broken English because I'm still learning. About the Lucy, for Lucy mission, we will observe at asteroid, right? So this asteroid will be on Trojan asteroid, what, or at the Kepler or offsite the solar system? That is my first question. And then my second question is, why only the Lucy will observe this at asteroid only? Because I believe that in our solar system, on our universe, we have so many asteroid. Or does it because Lucy will just fly by this at asteroid? I think that's all for me. Sorry for my English. But,
Okay.
but before that, thank you for the sharing. It was very amazing.
So
Okay.
so your question is why we have many near Earth asteroids, correct? And then why do we
Yes.
go to Lucy?
No, I mean the first question is, this at asteroid will be observed by the Lucy. Where is this asteroid? This asteroid will be on Trojan belt asteroid or at a Kepler or outside the solar system. The second is about why just at asteroid only. I think that's all.
Okay.
Sorry.
So, all right. So I'm pretty sure I understand both questions. So,
Okay.
so the very first asteroid is going to be the Donald Johanson one. Okay, that's in the main asteroid belt. The other asteroids are going to be sharing the same orbit with Jupiter. Okay, so they're not in the Kuiper belt. They're sharing the same orbit. So think of we launch Lucy, and on her way out to the Trojan belt, the ring that shares Jupiter's path, we're going to do a practice run on the Donald Johanson asteroid. You know, just making sure, hey, yep, this works. Yep, this works. You know, hey, this didn't work. Okay, let's re-engineer. Let's send some new programming up there. And then, so the other question was, I believe, is why this particular asteroid or set of asteroids? So really, you know, think about at the end of the day, it comes down, unfortunately, to money, right? You want to get the most value for your money. And so they said, okay, there's 500,000 asteroids out there. Which ones do we want to pick? And so you basically spend a long time, years, trying to say, okay, we do this, we get one. No. Let's do this. Oh, there we get three. No. Hey, I want 8. So basically you build your program around trying to really, you know, when you're buying something and, you know, you've got 1 unit of currency, you know, if somebody says, you know, I'll give you 1 for 1, okay. But you 1 unit currency, and I'm going to give you a whole bunch of asteroids. You're like, no, I want the whole bunch of asteroids. So really, it's about kind of choosing the diverse mix to get the best sampling, right? So if you go to the beach and you pick up a grain of sand, I could say, this grain of sand represents all the sand on all the beaches of the earth. Okay, is that true? Probably not. But if you pick up 8 pieces of sand, and you're going to realize, oh, maybe these 8 pieces of sand are different. So you need a bigger sampling. And that's really what it comes down to, is you need more samples. You just can't go to one asteroid and said, okay, that asteroid is made of this. The whole solar system is made of this. No, don't work like that. So if you can sample 8 and you can find the differences, that'll give you a better understanding of the diversity of the origins of the solar system. Does that answer your question? Cool.
Thank you so much.
You're welcome.
Okay, sorry, but can I ask just one more question?
Hang on, Titan. You have to wait in line because Miss Viania is first.
Okay, sure.
Okay, Vian, you go first.
Hi. So I would like to start that you were mispronouncing my name. I don't mind. It's okay.
It's okay.
My name is pronounced Vian, or you could just call me Denise because that's the easier part to pronounce.
Luis.
Where are you? Where are you from?
I'm from the Philippines.
Ah, okay. All right.
All right. Woo!
Sorry.
Yeah.
I think
So-
I'm also from Malaysia, yeah.
Yes, I'm from Malaysia.
Ah, okay. All right. Yeah.
Malaysia, Indonesia, Philippines. I love this group. Man, we gotta do more of these. We have to do more of these. I love this.
Okay, good. Okay, Vian, you can go ahead with your question, and then we go Titan.
So as for my question, this is in relation to self-teaching yourself. How do you stay motivated, or like how do you stay motivated to constantly self-teach yourself? Because my interests tend to fluctuate. So I worry that if I get super invested, that I will one day just lose interest or just burn myself out. Do you have any advice for that, for staying motivated?
Yeah, you know, it's taken me a long time to realize this. You need to take breaks once in a while. If you go through life expecting that you're going to be 100% motivated in a particular topic all the time, it's just not going to happen. Your interests are going to change. You know, myself, when I was young, I couldn't decide what I wanted to do when I was really young. I wanted to be archaeology. I wanted to be this. You know, I wanted to do a whole bunch of things, right? I just happened to kind of always go back to space and astronomy.
Yeah.
So don't beat yourself up if, you know, one day you just get up and I'm like, nah, I'm not motivated to do that today. Meaning a particular topic. That's going to happen. I took breaks and I had to sit back a couple of times and, you know, say, well, you know, what's motivating with me with this? So what always kept me interested, and it's kind of what I was telling the other young lady a minute ago, was I always went back to the beginning. What initially kept me interested? And for me, it was that video series that I mentioned, Cosmos. And you guys can go online, you can Google it or whatever search engine you guys use. And I still listen to some of those videos once in a while. And there's a video out there that keeps me emotionally grounded. And the video is called Pale Blue Dot. And it's not long. It's actually a poem. And he reads it, and it just keeps talking about, you know, humanity and our place in this earth and our place in this universe. So whatever keeps you grounded, and if you feel like you're losing interest in something, it could be something else. It could be animals. I mean, it could be whatever else it is. If you find yourself losing interest in something, kind of revisit why you became interested in the first place. And for me, I love history, and I always kept going back to, you know, early European Renaissance, you know, history. I love the old stories of merchants and, and sailing the world and silk trade and all those kind of things. And I love the stories of the Library of Alexandria in Egypt and all these kind of things. So knowledge always interests me, and I always came back to knowledge with people in astronomy. And so what keeps me motivated? You're not always going to be motivated. If you feel like you're losing interest in something and it scares you, just take a moment, reflect back on what originally kept you there. And as you grow older, you may find that, you decide it may not be the path for you, and that it may not be. Or you could take a break from it, and then all of a sudden something exciting happens and you're all the way full throttle. So staying motivated is hard. Don't beat yourself up if you lose motivation once in a while. It happens to everybody. It took me a long time to learn that. Give yourself breaks. You don't have to be 100% on a topic every single day. Take breaks, and always go back to what originally got you interested.
Yeah, I agree with you. I mean, like, I experienced that a lot as well. And I take breaks in between, and it can be very tiring. And also, it can be very competitive as well, and it can be overwhelming for us. But worry not, space is not going anywhere. It's gonna be there forever and ever, and you have all the time in the world to catch up. And don't feel overwhelmed, don't feel intimidated. And as for me, my trick is always to, of course, have a break and then try to do something else first, and then it will, automatically drives me back to space. And I also, in my career, I've done like how many career change I did infrastructure, military, I did education, climate change, environment, but space is the only thing that always I always come back to.
Yep.
So
same here.
yeah, I mean, like, and people in the space industry, or in the space community, we all have it. The industry itself requires you, mostly it's like multidisciplinary. You don't just specialize in one thing, you have different backgrounds. Like, for example, an astronaut, they have a undergraduate in something, and then like their master's degree in different thing, and their PhDs in completely different things, and their postdoctorate is so sometimes they have double bachelor, sometimes they're also a doctor, they're also engineer, and they're also a geoscientist. So it doesn't always have to be from one discipline, and there's no such thing as like pure just space, but there's different things that you can do, and then it will still lead you back to space in the end. So that's what I found useful as well. Like, like even biotechnology, like biotechnology, and that's also useful for in terms of like microgravity research, or farming, agriculture. As I said, like, it's going to be space farmer is going to be the most desirable, future job, number one future job. So yeah, if you find it like, if you're tired at some point, have a break, but do something else, and then everything will lead back to space.
And I'll just say this, and I will let Titan go here. Don't be afraid to have multiple disciplines. If you love plants and flowers, go learn plants and flowers, become a botanist. We're going to need botanists in space, so exactly. So, find something you do. You love animals, be good at, animals, because eventually we're going to need to farm animals in space, even if it's little teeny fish. So, don't be afraid to have more than one interest. It'll probably serve you very well.
I think Tobias is also here, and he's fascinated with space farming. But Titan, didn't you want to ask a question?
Sure. Does the engine? Does the engineer in NASA learn origami to make the, Lucy's wings? Solar panels. so it can like the faults and stuff.
For the panels.
Yeah, and others.
So I heard NASA engineers developing the solar panels. What was the question?
Origami, like do they have to learn origami, the Japanese techniques of, you know, all the arts and craft origami for the solar panel?
Okay, well, if they work for me, they do.
Yeah.
Yeah, if they're on my team, yeah, they need to learn origami. You bring up a very interesting point, Titan, and as we keep talking about learning different disciplines of things, and I'm sure the origami concept is very present at NASA, because they constantly have to learn how to fold things in different ways so that they can unfold in certain ways. I'm not sure if they're required to learn it, but I'm sure it's a really good skill for an engineer to have. That's for sure. And if they're ever on my mission team, I'm going to say Titan made me say that you need to learn origami. No, but it's a really good skill to have, whether or not they actually practice origami, but they practice basically origami on big machines. So that's an interesting question. I'll try to find out.
Yeah, I think a lot of missions are definitely using origami concept, because you have to
Absolutely
compress everything in the rocket. That's first of all, and then as you launch it, and then in space it gets unfold, right? So I think I feel another person raising their hand, but I can't locate the name. Tobias, did you want to ask anything about Lucy, or anyone else from the audience? If not, I think it's time for us to part, because it's 12:45 and it's lunchtime, and we all want our lunch, and you need your sleep for sure.
Yeah, I'm 12 hours behind you guys, so it's midnight for me, past my bedtime.
Yeah,
but I'm always here for you. Always here for you.
Thank you so much. I hope everybody gained, like lots of knowledge from this session, learning more, not just about the mission, but yeah, and the background of working in the industry itself, or astronomy. And if you join our WhatsApp group, I share information daily or in every few days. So you can also self-learn, and that's very important, right? From websites or from YouTube, so even from the webinars. Just a bit tricky if the good webinars from the US, it's always our midnight or 1 o'clock in the morning. So that's also tough. But whenever there's a recording, we will share it as well. But thank you so much, Todd, for your time. It was very lovely to
Thank you.
Have you presented all of the videos and the details. So we will see you again.
Absolutely.
Either for DART or James Webb, or an update on Lucy next year, because it's going to be, we will continue to see you. I mean, the mission is 12 years. So it's pretty long until we have some data download.
All right, then. It's a pleasure meeting you all. If you guys really want to ask me something else, you can certainly phone it through Ann. I'd be more than happy to take questions, off camera too. So thank you.
Okay. Thank you so much, everyone. Have a good weekend and have a good Saturday. Good night.
Okay.
Bye. Good day.
Bye.
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 Bye. Actually, we forgot to take a picture.
Yeah, I was about to say that, but never mind.
You were supposed to remind me.
I was typing in the chat. Okay, fine.
That's your homework for the webinar.
I'm sorry.
Okay, well, it's okay. We'll do that after. Bye. See you mid-November. We'll have more, but you know, I'll just we'll post the updates in our Instagram. Bye, Titan. Bye, Vian. Tala, Ahmad, Jeliza. Thank you.